I think so.
All right. Well, sorry I can't be there. I'm getting ready to see my daughter.
Let me.
Sorry. Go ahead.
Okay. Yeah. Then yeah. I'll get started. So I need to share my screen first, right?
Yeah. So I can do that too if you want, if it's easier. I can just share the.
Am I sharing my screen now?
Oh yeah, it looks great. Yeah.
Okay. Cool. Yeah. Is it big enough?
Oh, it's plenty big. This looks great.
Okay. Cool. Yeah. I'm gonna talk about hashing, especially for IoT. So first, hash basics. So a hash function is any function that can be used to map data of arbitrary size to fixed size values. And the value returned by a hash function are called hash values, hash codes, digests, or simply hashes. The values are usually used to index a fixed size table called a hash table or hash map. Use of hash function to index a hash table is called hashing or scatter storage addressing. And here's a small phone book as a hash table. Yeah, so you can see the names, which are the keys, get hashed to some numbers through hash function. And the number of interconnected everyday devices continues to grow. So, and the hash functions also has some use for security concerns. So, yes, so, and most of these devices in IoT collect data, and the data collected is stored in online using web services that sometimes run without any specific security and privacy concerns, and which is a concern. So one way they do the security is open standard authentication, OAuth. It is a common protocol which allows social services to communicate with each other and providing a safe way to share personal data. It offers a web application framework which gives third parties access to their resources without sharing confidentials with their clients. So I think this one's like you can use your credit card information saved in your Google account on some other shopping website. I think this is kind of like that.
Yeah, I think the way it works is I believe it, and I might be wrong about this, but I believe it uses the OAuth protocol to create a temporary token, and that temporary token is provided by the credentialing organization to the other company. So what passes through the internet is just a token transfer handoff, and then to transfer your credentials to the let's say you've got a vendor, you'd send those credentials over over a secure channel that's been established between the like Google, for example, to your online merchant.
Okay. Yeah, and then the second one is a form-based authentication form-based. Yeah, that one is a online networked computer system based on the web and the internet. I think this is like you fill up a form, maybe. username, password, and then pass the information to the website and then get the data. Yeah, so I think this is like that. Yeah, the third one is the REST, representational state transfer. Is an architectural style of software which defines a set of constraints to be used to build web services. I think this one involves REST API, stuff like that. Yeah. Okay. So the IoT is about to become the next major technical hype. Every day, new services appear which make use of IoT devices. These new services are using web-based storage, and the IoT devices are beginning to interact with such web storage. So the two problems arise. One is the privacy and control of the data collected. Two is low bit authentication for end-to-end devices. So I think the low bit authentication here mainly means you don't want the security process to be too long. You don't want it to take too much time to send the private information from device to device. So it's better to be a low bit authentication. Okay, any comments or thoughts?
Oh yeah. So I mean, for the problem is that a lot of these devices, they don't have the ability to do a lot of different hash algorithms. And so usually what you end up having is you end up having to do like a low. One of the reasons why they, so I guess to back up a little bit, the reason why they use OAuth and some of these other applications is because they've got a low risk token transfer between the user, the merchant, and then the actual credential storing provider, which is normally like Google or some other kind of company like that. The same thing happens with embedded devices. The embedded device can't put across the internet a high, like a high bit rate hash algorithm or security algorithm, because the cost in terms of battery life and processor usage is too high for the processor to usually do. So it will do a like a low data rate security algorithm like the SHA-1 or SHA-256 for like a small amount of message passing to a credentialing service like Google, or like maybe like a centralized server. And then once you've like sent across like a simple request, that other device will handle all of the setting up a secure SSH style or some kind of like a secured cryptographically secure channel to whatever device or organization you want. So for example, if you've got a temperature sensor, you can you'll encrypt your packets, and they'll go to a centralized location, and really the encryption is only there, and the actual method for encrypting is designed for is usually like it's like a one-time password, and you'll usually change your password on a regular basis, because you can't use the same keys over and over again. In a lot of these cases, you can actually end up having that data decrypted. It's more difficult, but most of the time, the sensors and for low value targets, it's not really something that you're worried about. You're really worried about like mass surveillance, as opposed to loss of one particular device's information.
All right, thanks.
So sorry.
Okay, so next section is hash algorithms. So some hash functions such as a message digest algorithm, MD, and secure hash algorithm, SHA, SHA 0 and 1 were widely used. However, they are broken in practice. So, for example, here is a short horror movie, and the title is "Cracking a 2001 Arrow MD5 Password Hash Using 2016 Hardware." So let's watch it very quick. So it's about 1 minute, I think. Okay, I didn't. Okay, sorry. Okay, I'm sorry. Sorry about that.
That's okay. Oh, I didn't realize. Oh, Hugh Jackman was in Hackers.
I'm sorry.
Oh no, it's fine. I was just noticed that Hugh Jackman was in Hackers. I didn't realize that was him. Much younger Hugh Jackman.
Yeah, so that video just used OCL hashcat to hash the MD5 password. So OCL hashcat is a GPU-based multi-hash cracker using a brute force attack implemented as a mask attack, combinator attack, dictionary attack, a hybrid attack, a mask attack, and a rule-based attack. So brute force attack is like you just guess all of the possibilities and then you try everything. And then, so if you get one, then you get it. So and there are some other techniques, other attack methods. So that's one of the reasons why MD5 is not secure anymore. Okay, considering the potential danger of being attacked for SH2A2, the National Institute of Standards and Technology started the NIST hash competition to develop the future hash standard SHA-3. So yeah, like so SHA-2 is not secure anymore. So NIST started a competition to develop a hash standard SHA-3, and SHA-3 the competition is over, and the winner is KCOC. So SHA-3 was known as a KCOC and is a hash function designed by Guido Bertoni, John Damon, Michael Peters, and Gilles van Esk. MD5 and SH3 have been shown to successful to attacks So is sh1 mean theoretically. So in October 2012, Kakak won the NIST hash function computation and is proposed as the SHA-3 standard. It should be noted that it is not a replacement of SHA-2, which is currently a secure method. Currently secure? Maybe not theoretically, I'm not quite sure, but still not quite secure. As the hardware develop, like the CPU, GPUs develop, maybe getting faster and faster. Yeah. So overall, Kakak uses the sponge construction where the message blocks are XORed into the initial bits of the state, and then inevitably permuted. So let's look at this article. It's called High Performance and Low Power Hardware Implementation for Cryptographic Hash Functions. It's an article published in 2014 by Yulong Zhang, Zhou-Hee Kim, Ken Choi, and more. So this article talked about SHA-3. So see the algorithm used absorbing first and then squeezing. So you can see they use some bitwise operations. Later on you will see. And they did some manipulation with the original data. And the permutation, they use the permutations. First, they initialize the state, the input, and then they separate it into two pieces. One is BR, the other is C. And then they absorbing, and then they squeezing. So, and here's the squeeze function they used. I think this is the two bars are they OR operator?
I think it's like XOR, or it's either or.
Oh, I think that's OR. I think that's OR operator maybe, and the plus circle is XOR operator. I think that's my guess. Okay, and the three less signs are what?
Rotate.
Rotate.
So shift rotation. So that's a shift left rotation. By K.
Those are unsigned rotate, unsigned shift, right? I think
yeah, so that's a left hand. So it's a shift left rotate K.
Yeah, and so they use lots shift permutation and some other bitwise operators, and yeah, so that's how they do it. Yeah, and so. Okay, and there's another article about SHA-3 for IoT here. If you want to read, you can read this one. They also mentioned this SHA-3 absorbing and then squeezing sponge algorithm. Yeah, some other stuff here. Yeah, and at the end, they also mentioned another like libdisco and Kakak for symmetric key encryption. If you are interested, you can read this more. I mean, later. And also, the last thing I want to talk about is the Python hash lib. It's Python has some hash functions, like it has a hash function in it. So, and Python uses, I think Python started to use SHA-3 like, yeah, see, hashlib now uses SHA-3 and shake. So they are starting to use some newer hash functions. Okay, that's all for my presentation. Thank you.
Thank you. Yeah, I actually had a project where I needed to use I needed to have built-in. Well, there's two things. One is that ARM actually has a crypto library and crypto hardware that does all those math operations that I have to go through to make to run the algorithm. To do that in software is pretty easy to do. But if you want to do like high bit rate, like wireless communication or encrypt your data stream, that requires normally like a hardware-based crypto algorithm that's actually baked into the processor itself. Because otherwise it takes, I mean, you saw there, like it took like maybe like 6 or 7 times, maybe like 3 or 4 operations to actually run that algorithm per message or per encryption operation, which for doing real-time or high uptime critical communication is difficult to do. So like ARM, for example, has a crypto cell that they offer to embedded manufacturers as something that they can actually purchase and then license and then put that into their core chipset. So there's a couple of devices that have these crypto cells in there, and what those do is they do something called like a root of trust style security paradigm. And what that means is that the device itself has a piece of cryptographically secure information in it, and it will use that to secure and verify new firmware loads, as well as communications to a trusted third-party device. So this is what happens when you get like a Windows update, and you have to get it verified by your motherboard of all things, because that's where the root of trust actually lives, actually in the hardware of your computer, to verify that your computer is who you say it is and that you can run that update. So it's really interesting stuff. There's this really weird dance right now between security and then the right to repair and right to work with your own hardware, and then also like how much security do you provide and how much do you obfuscate and hide from the end user. So in a lot of these cases, these are becoming opportunities just to lock down hardware even more, and so you can't do things like hack your own devices, load your own custom firmware, or really control your own devices. The flip side, though, is that if you do have right access to that, you have complete control over your device, and you can basically prevent malware from infecting your computer, because they have to have that root of trust that's built into the cryptographic engine in your hardware. And so it makes it more difficult to get some of the really nasty, to do some of the really nasty like hardware persistent viruses and security threats that were really common in the 2000s, 2010 era hardware. Things like you'd have a computer that has like a virus in it, but you can't get rid of it because once it's embedded in the hardware itself. So things like that. So what I'm going to talk about a little bit today is a project. So okay, so let me roll back a little bit. Last time we met, we talked about, I think I actually showed off well, this is the board, but I showed off this guy in digital form. This is I'm calling this is actually a part of a company that I helped start up with another guy named Daniel Ashcraft. And the idea is that we're going to basically build open source hardware for home gardening and vertical gardening and then we'll produce software as a service for managing and doing like large scale installation viewings for things. So the idea would basically be like you'd have like maybe like if you're a single home user, you probably would have like maybe two or three of these, and you'd buy them once, and then you'd be able to hack them if you wanted to, or you could run our software, and it doesn't cost you anything past your initial purchase. If you're a big company that has like maybe like 40 of these or more, we'll provide a software as a service subscription model for managing like a giant fleet of these things. So unless you've got like 40 of these, or you want to have like long-term history for like a year's worth of data stored and recorded and managed, then you don't really care. But the cool thing, though, is that we're looking at basically getting the cost point. So roll back again. This isn't there's a whole bunch of other options for temperature humidity sensors. This is kind of like we did this route because we wanted to have a source control over the whole design, and I wanted to build one, so I did. And so this started off as a dev kit that used one of these Wemos devices with a temperature sensor they could buy off the shelf. Plugged it together. We did some development with it. We decided that we kind of like this form factor, and so I basically took all that and shoved it into this little board. And I can probably get smaller than this, but I haven't done so yet. So let me show you guys so you know what I'm looking at. This was all done in KCAD. KCAD is an open source layout, and okay. There's open source like PCB design software, and okay. And this is the actual schematic itself. It uses the only couple interesting things about the design. It's a pretty basic design. There's not a lot special about it. It basically uses a ESP32C3 Mini or ESP32 Pico Mini. The only interesting thing about the C3 is that it's actually a RISC-V processor. It also has a built-in USB stack, so you can actually like talk direct USB or USB to the device if everything's active and ready to go. I actually have on the board like 3 different temperature sensors or foot pads for it. The BME 2080, BME 280, the SHTC3, and the SI 7020. And on top of that, I also have those pads are actually also used by other vendors. And so they're pin and chip compatible with I think a couple other vendors worth of temperature humidity sensors. And this is important because right now we're in a supply crunch for almost all hardware. So for example, like I ordered temperature humidity sensors like the day of. I got this schematic finalized and ordered. And then like 2 weeks later, I went back to purchase another round of them, and everything I'd ordered for certain key components were out of stock. But because I had laid it out for so many different options, I was able to actually find at least another option I could purchase. So that was good. So it's pretty simple design. It's got like it's got an RGB LED on it. It takes in 5 volts from the USB plug, and it level shifts that down to 3.3 volts. And I think at some point we're going to basically do a battery powered version of this. But for this initial product, we're looking at just the bare minimum, get out the door kind of price point. And even at this point, we're still looking at like the device in total is probably going to be like $25, $30 per device, which is higher than I'd like, but prices are not kind for small volume products like this. Let me show off the actual layout. Might be interesting. Okay. So this is the actual PCB layout. It's pretty simple. You can kind of see the gist of it. I had to make some of the. I actually got to go back and make some adjustments. Whenever you make a board for the first time, it almost never works exactly like you expect it to. And so, and this was and this was just like that. So. There you go. So what we're looking at is just a layout and trace pattern for everything. Let me change this. Change that. Okay. Yeah. So the only kind of interesting thing about this was to do the layout, it kind of required, this is a 2-layer board design. So kind of figuring out like where things should go and how the layout and flow of the board should go and what the shape of the board. It's one of those things where you kind of like put something on the ground and you kind of play around with certain function to see like, does this go right here or should I move it over there? And then having to kind of go back and forth between parts and availability. So like this section over here was all these 3 sensors had to be really close to each other because they all shared the same I/O lines, and then they also shared the same power lines too. And then I kind of just naturally fell in place that like this is the JTAG controller, JTAG interface. It made sense to put it here just because that it was lined up perfectly with the I/O lines here. The antenna, which is up here, it turned out that like antennas have to have a clearance on either side of them so that they don't have any interference from metallic surfaces. So it turned out that it actually worked out well to keep the shape of the device in this kind of like oval shape, and that I could use the tabs on either side to protect the antenna from bumps and physical damage. And so we got the LED packaged on the bottom here, and it's just a RGB LED with that's the way it works is that it looks like the voltage is sunk to ground through the I/O pins, and so it goes through the resistor, and then it usually and that's how you turn it on. It's got 3 volts across it through the resistor, and then these I/O pins here just sync it to ground. And I probably need to remove these until I get the actual version that actually can use it, because I think the USB standard actually puts I think like 3 volts or 5 volts on the D+ D- line, and I think these are 3 volt. I think these are 5 volt tolerant on the ESP32, but they don't. But it's not always the best idea, and it can't be used anyways. So until I can get a version of this module that can handle the I/O from the USB, it doesn't really do me any good. And so then I've got the TXRX lines for communicating, debugging, and programming. The ESP32 line actually has a built-in bootloader that comes from the factory, pre-programmed. And so when I get these devices, they've actually already got a bootloader in them. And so all you have to do is flash it with your firmware the first time, and then after that, it's good to go. A couple of mistakes I made on this board, which isn't a surprise, but I really wish I had added in a clear to send, a CTS, and a RTS line on the TXRX ground 3.3 volt line, because that would have allowed me to take advantage of their automatic bootload functionality that ESP32 already has baked in. And that allowed me to use a single cable to do all of my bootload programming and all that. I got clever, and whenever you get clever, I always make mistakes. So there's a downside to being clever. And I created a single button to both both reset the board as well as go into bootload. And the way that worked is that if you do a short press on the button, it will go into the bootload mode. But if you do a long press, it'll reboot the device. And if you power it on normally, it'll just reboot the device normally. The problem is that it uses a resistor divider network, and it also uses a capacitor and the charge rate of the capacitor to configure the timing for the whole circuit. And so it's very dependent upon temperature and upon the value of your resistors and capacitors. And because it's like a couple of milliseconds timing interval for all this, it needs to be tuned. It'll also have to be tuned per device and per configuration. So long term, it's not a really great idea. It seemed like a better idea at the time. And the other thing is that I'm probably going to take out this JTAG interface and replace it with something that's a little bit more board real estate friendly. This JTAG interface is going to be used by me like maybe once. I'm looking at, for mass production, I'm looking at using the JTAG interface to program like maybe 10 to 20 devices at a time. And so to do that, I need to use a JTAG interface and put them in a chain. And so what that means is that the input and the output are tied to the device after it. So what it looks like is you've got like a chain of devices, and the input's tied to the output of the one before it, and the output is tied to the input of the one in front of it. And so what you do is when you program the whole lot, what you do is you plug into one of the devices, and then you would send a command to program basically X number of devices in a chain, which you would know beforehand. So if I've got maybe like 10 in a panel, then I would be able to program an initial load into the entire panel all in one go, which is really nice for designing for manufacturability. I also need to panelize this, which means that I basically take this and I copy it X number of times for how many I can fit into a panel. And then when I get it ordered, I can run this through a pick and place machine, and the pick and place machine will be able to do like the entire panel at a time. So for example, if I have like 10 of these in the panel, it'll be able to do 10 at a time. Then you take that panel, you run it through an oven. The oven has a temperature ramping profile, and so it'll ramp the temperature up at a slow rate, and then it will reflow or melt all the solder on the board, and then it will go through a cooling period, and it'll cool off the board. And then what I'll get at the end of that is I'll get a panel with 10x boards, and if I design the panel correctly, I'll be able to do programming in that panel directly. which would be nice, because then after that happens, then I have to route out the each individual board or break them out because they've got a v-score on them. So that's kind of where that's at. Does anybody have any questions before I jump into the next part?
How do you connect this to? Do you connect this to your phone?
Yes. So the module here is a Bluetooth and Wi-Fi module. So when I load, it'll actually allow me to send Bluetooth as well as wireless Wi-Fi packets over the air. So we're also developing an app to read these directly, but the protocol is also open. So I think it'll actually work with a couple of other like MQTT based or I think it's web RTC.
HTTP?
Yes, HTTP. And it'll also do Bluetooth as well. So you can actually report back the characteristics directly from the Bluetooth, or we can actually send it across the internet through the Wi-Fi interface.
Cool.
Mm-hmm. Yeah. So and that's I mean, it's nothing really new or special. There's other companies that do something very similar. But the cool thing is that we designed it, we developed it, and we're designing it for like a wet or humid environments. So I've got a couple of processes for conformal coding the whole thing, and then adding some artwork to it as well. So, and I can kind of show you, like, this is what the boards look like. This one over here is from OSH Park. This is the I think the Midnight Black version. You can actually see like the zooms in and focuses, which it's not. The copper is actually covered by a, you can see on the back a little bit easier. The copper color is actually has a clear solder mask, and then the PCB itself is a there you go. The PCB itself is actually a black fiberglass material, and then they did a gold ENIG, a gold-plated ENIG copper coating on it, or coating on it for the pads. And so when this guy, when it goes through pick and place and reflow, looks like this guy. So you can see here that if you've got a fully populated board, let's see, there you go. So fully populated board with a LED on one side and then USB on the other, power modules on the top, and then the reset button, which doesn't quite work like it should, on the opposite side. And then the programming header is, or the serial header is populated currently on this version. I also ordered from Seed Studio, which has a PCB fusion option, and this is what I got from them. Their boards were nice. They're much cheaper than what I got from OSH Park. Let's see if I can get it. I think the focus is, there you go. And the quality looks pretty good. I need to build some of these up. My plan is to build up 15 to 18 of these in total for prototyping. And let's see if I can get this one. Yeah, so the OSH, I'm really happy with how the OSH ones turned out. The only thing I don't like about it is that they didn't route out the corners, so that I've got these sharp pins sticking out. Where these over here, they fully routed them out and smoothed them out. I can take a Dremel to clear these off, but it's just kind of a pain in the butt. The only other downside was that the ones from Seed Studio and from the Fusion service, they took a long time to get to me from from China overseas and into my hot little hands. Took about like a month, give or take, a little bit more than a month. Where these where I got from OSH Park took about 2 weeks. Because what literally would happen is I ordered these first and I got tired of waiting. So I ordered these, and then guess what happened? By the time I got these and I got the day after, these showed up. So, but it worked out. I wanted to try multiple vendors anyways to kind of get a feel for, because I'm used to using other like higher end vendors. I've not used a lot of open source vendors. So this was kind of a learning experience as well. I also got some interesting things. I also ordered some stenciling. So the way these things are if you're familiar with how like t-shirts are screen printed, it's almost the exact same thing. What they do is they take a board like this, and then they place over it a stencil like this, and the stencil maps directly on top of the solder pads. So you can kind of see how these, well, if I turn the right side up, you can see how like these line up directly, the two of them. And then you use basically kind of a squeegee to like push into the open slots the solder, the liquid. Basically, it's they're little micro balls of solder, and then a liquid flux. And so what that does is it kind of produces, it actually puts on to the board just enough material to allow it to reflow, and then the parts to get kind of sucked into and like attached to the board, or attached to the board when it all solidifies. So this was a stainless steel version. It was about, I think, like $14, which is really cheap and nice. These are really nice board, really nice stencils. I also ordered a Mylar version, and it is also nice. It was just a little bit, I need to be careful with it. Yeah, it's also nice, but it's a little bit different. So this is the Mylar version. This is the one we actually used on the first 2 boards. But you can kind of see it's the same setup. And so, yeah, that's kind of the process of what I went through, and kind of the process for manufacturing these devices for prototype quantities. And overall, it's been a good experience. I really enjoyed the checking out these different vendors. And if I can, let me put some links in the description. Yeah, and I mean, so this is kind of silly, but like, whenever you buy parts from, in this case, DigiKey, you basically end up having like this box full of like little baggies. So it's just like an endless supply of baggies. And so like for example, the manufacturing process just kind of goes like, I end up having just like printouts for all the hardware. And then that's about it. So basically it's kind of like it's kind of a whole process. You print out all the documentation, you kind of go through it piece by piece. You organize all your baggies, you write down what you need, and then you put it all together. Any questions?
So for the buttons, you said there was a short push and a long push, and then there was something in the middle. So how can the user tell if it's if he or she pushed at the right amount of time?
Well, that's the other problem, and one of the reasons why it wasn't a good idea. You can't really. when I first put these boards together, the button didn't really work. It was stuck in program mode because of the way it would power on. So I had to add in an extra resistor to get it to even run the program that I programmed it with. And so it sounded like a good idea at the time, but I didn't get a chance to really test it out. So I'm gonna have to go back and revisit that option. I may just remove the whole thing together because there's not really need to reset the device. I can just pull the power and plug the power back in. So that's kind of what happened and why it is the way it is. So it was a mistake.
But it's an interesting mistake.
Mm-hmm. Yeah, I'm actually of all the boards I've done, I was actually kind of like weirdly successful the first time around. I was like, everything turned on, the thing blew up, everything like powered on correctly. All the buttons looked good. I was kind of worried, so I was kind of glad I found something that was a problem. So I guess I can show you what the current prototype looks like. It's a kind of a pile of wires, but so this is what it actually looks like when I'm actually programming it. This is actually a TTL logic RS-232 serial cable. And so what happens is that I'm using the 2 lines for power and ground, or well, 1 from ground and then 2 TXRX lines that I'm actually to actually get this thing to run, I actually have to use a third. I actually have to use the power line coming from the module to short out the button. So what I'm going to do eventually is I'm going to actually solder this directly onto the board, but you actually have to kind of like poke the resist or the button just right, and then it'll boot up the device. So the good thing is that after I get it programmed and I add in a resistor to keep it from resetting all the time, I'll actually just be able to program it over the air. The ESP32 module has a built-in bootloader with a over-the-air option, and so I can actually just push firmware updates over the air. So that'll happen. That'll be what I'll probably load one firmware load onto it initially, and then after that I'll just program it with by pushing firmware updates through remotely, which I need to get working anyways before we ship. But oh yeah, so Daniel jumped on the call for a little bit and then dropped off again. But he's the other guy I'm working with. He's doing the software and all the heavy lifting on the business side, because I just build things. So, any other questions? Well, cool. Well, thank you for joining us for this afternoon. I'm going to stop recording. Does anybody have any questions? Well, I'll stop recording.